The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Today we're going to start with a simple problem that many of you may have already encountered. For example, when you got a student loan, or if your family took a loan out on your house, a home mortgage loan. And it's the problem of pricing an annuity. An annuity is a financial instrument that pays a fixed amount of money every year for some number of years. And it has a value associated with it. For example, with the student loan, the value is the amount of money they gave you to pay MIT. Then later in life, every year or every month, you're going to send them a check. All right, and you want to sort of equate those two things to find out, are you getting enough money for the money you're going to pay back monthly sometime in the future? So let's define this. And there's a lot of variations on annuities. But we'll start with one that's called an N-year $M payment annuity. And it works by paying M dollars at the start of each year. And it lasts for N years. Now, usually N is finite, but not always. And in a few minutes, we'll talk about the case when it's infinite. But this includes, home mortgages where you pay every month for 30 years. Megabucks, the lottery. They don't actually give you the $1 million. They give you $50,000 per year for 20 years and call it $1 million. Retirement plans, you pay in every year and then you get some big lump sum later. Life insurance benefits, and so forth. Now, if you go to Wall Street, this is a big deal. A lot of the stuff that happens on Wall Street involves annuities in one form or another, packaging them all up. And in fact, we'll look at later when we do probability, it was how these things were packaged and sold that led to the subprime mortgage disaster. And we'll see how some confusion over independence when you look at random variables led to the global recession, a real disaster. Of course, some people who understood how all that worked made hundreds of billions of dollars at the same time. So it was sort of money went from one place to another. So it's pretty important to understand how much this is worth. What is this instrument, a piece of paper that says it'll pay you M dollars at the beginning of each year for N years, what is that worth today? For example, say I gave you a choice, the megabucks choice, $50,000 a year for 20 years or $1 million today. How many people would prefer the $50,000 a year for 20 years? A few of you. How many would prefer the $1 million right up front? Yeah, much better. Okay. Always better to have the cash in hand because there's things like inflation, pretty low now. Interest, you can put the money in the bank or invest it and make some money, hopefully. So the $1 million today is a lot better, which is why the state pays you $50 grand a year for 20 years. It's better for them, and they call it $1 million. So that was pretty clear, but what if I gave you this option? 700 grand today or 50 grand a year for 20 years. How many people want the cash up front? 700 grand only. A few. How many people want 50 grand a year for 20 years? All right, we're almost, that's pretty close to halfway. How about 500 grand today versus 50 grand a year for 20 years? How many want $500,000 today? Well, a lot of people like the cash. It's this kind of a time. You have the recession. It's a disaster on Wall Street. On Wall Street, they like the cash. How many want, instead of $500,000 up front, 50 grand a year for 20 years? All right, now we're about halfway. All right, well, that's pretty good. So we're going to find out what you should pay, or at least one way of estimating that. Now, to do that, we got to figure out what $1 today is worth in a year. Okay? And to do that, we make an assumption. And the assumption is that there's a fixed, we'll call it an interest rate. It's sort of the devaluation of the money per year. We're going to call it P. Later we'll plug in values for P. But you could think of it as like 6%, 1%. You know, it's the money, if you put money in a bank, they'll give you some percent back every year. And of course, the fact that different people have different ideas of what this would be allows people to make money on Wall Street. As we'll see, a slight difference in P can make big differences in what the annuity is worth. So for example, $1 today is going to equal 1 plus P dollars in 1 year. Similarly, $1 today, how much is that going to be worth in 2 years? Say that P stays fixed, same over all time. 1 plus P squared. Because every year you multiply what you got by 1 plus P, because that's the interest you're getting. All right, we'll think of it in terms of interest. In 3 years, $1 today is worth 1 plus P cubed in 3 years, and so forth. All right, now what we really care about is what's $1 or M dollars worth today if you're getting it next year. So we need to sort of flip this and back the other way. So what is $1 in a year worth today in terms of P? So if I'm going to be paid $1 in a year, what would be the equivalent amount to be paid today? 1 over 1 plus P. Because what's happening here is as you go forward in a year, you just multiply by 1 plus P. So 1 over 1 plus P turns into $1 in a year, being paid in a year. All right, what is $1 in a year in 2 years worth today? 1 over 1 plus P squared. All right, so $1 in 2 years is worth this much today. All right, well now we can use this to go figure out the current value of that annuity. We just figure out what every payment is worth today and then add it up. So we'll put the payments over here and we'll compute the current value of every payment on this side. So with the annuity, the way we've set it up is it pays M dollars at the start of every year, so the first payment is now. So the first of the N payments is now. And since it's being paid now, that's worth M dollars. There's no devaluation. The next payment is M dollars in 1 year. And so that's going to be worth M over 1 plus P today. And the next payment is M dollars in 2 years. That's worth M over 1 plus P squared. And we keep on going until the last payment. It's the nth payment, so it's M dollars in N minus 1 years. And so that's going to be worth M over 1 plus P to the N minus 1. All right, so we can compute the current value of all those payments. Then the annuity is computed, the value is computed just by adding these up of all the current values. So the total current value is the sum, I equals 0 to N minus 1, of M over 1 plus P to the I. And that is the total current value. That's what you should pay today for the annuity. Any questions? What we did here? All right? Well, of course, what we'd like is a closed form expression here. Something that's simple so we could actually get a feel without having to add up all those terms. And that's not hard to get. In fact, let's put this sum in a form that might be more familiar. This equals, we'll pull the m out in front, and let's use x to be 1 over 1 plus p to the I. And so x equals 1 over 1 plus p. All right? And I wrote it this way because this might be familiar. Does everybody remember that from, I think it was the second recitation? Anybody remember the formula, what this evaluates to? The sum of x to the I, where I goes from 0 to n minus 1. Remember that? 1 minus x to the n over 1 minus x. All right, in the second recitation, I think, we proved that this equals that. What was the proof technique we used? Induction. Okay? All right. So, all right. So, in fact, there's a theorem here. For all n bigger than or equal to 1 and x not equal to 1, we proved the sum from I equals 0 to n minus 1, x to the I equals 1 minus x to the n over 1 minus x. Okay, and so this is a nice closed form. No sum anymore, just that, which is nice. Now, induction proved it was the right answer. Once you knew it, we gave it to you. Using induction to prove that theorem wasn't hard. What we're going to look at doing this week and next week is figuring out how to figure out this was the answer in the first place. Methods for doing that, to evaluate the sum. And there's a lot of ways that you can do that particular sum. Probably the easiest is known as the perturbation method. And this sometimes works. Certainly with sums like that, it often works. And the idea is as follows. We're trying to compute the sum s, which is 1 plus x squared plus x to the n minus 1. And what we're going to do is perturb it a little bit and then subtract to get big cancellation. In this case, it's pretty simple. We multiply the sum by x to get x plus x squared plus right? I've defined s to be that. X times s, well, I get x plus x squared and so forth up to x to the n. And now I can subtract one from the other, and almost everything cancels. So I get 1 minus x times s equals 1. These cancel, 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 minus x to the n. And therefore, s equals 1 minus x to the n over 1 minus x. All right, so that's sort of a vague method. This gets used all the time in applied mathematics, and they call it the perturbation method. Take your sum, wiggle it around a little bit, get something that looks close, subtract it, everything cancels, life is nice. And all of a sudden, you've figured out the answer. OK, so getting back to our annuity problem, we can plug that formula back in here. So the value of the annuity is m times 1 minus x to the n over 1 minus x. We'll plug in x equals 1 over 1 plus p. And we get m 1 minus 1 over 1 plus p to the n over 1 minus 1 over 1 plus p. Just plugging in. And now to simplify this, I'll multiply the top and bottom by 1 plus p. And I'll get 1 plus p minus 1 on the bottom just gives me a p on the bottom. I have a 1 plus p on the top minus 1 over 1 plus p to the n minus 1 all over p. All right, so now we have a formula, closed form expression formula for the value of the annuity. All we've got to plug in is m, the payment every year, and the number of years, and then p, the interest rate. And so, for example, if we made m be $50,000, as in the lottery, we made n be 20 years, and say we took 6% interest, which is actually very good these days, and I plug those in here, the value is going to be $607,906. All right, so those of you that preferred 700 grand, if you assume 6% interest, you're right. Those of you who preferred 500 grand, no, you're better off waiting and getting your 50 grand a year. Now, of course, if the interest rate is lower, well, that changes things. All right, that shifts it even more. The annuity is worth even more if the interest rate is lower, all right, if p is smaller. In fact, say p was 0. Say the interest rate is 0, so $1 today equals $1 tomorrow. Then what is the lottery worth? $1 million. All right, and the bigger p gets, the less your payment is worth. All right, any questions about that? Okay, what if you were paid $50,000 a year forever? You live forever, or it goes to your estate and your heirs, $50,000 a year forever, or $1 million today. How many people want the $1 million today? How many want 50 grand a year forever? Sounds good. You know, 50, that's an infinite amount of money, sort of. It's not as good as it sounds. Let's see why. So this is a case where n equals infinity. And so I'll claim that if n equals infinity, then the value of this annuity is just m times 1 plus p over p. Let's see why that's the case. You know, it sounds hard to evaluate because it's an infinite number of payments. But what happens here when n goes to infinity? What happens to this thing? That goes to 0 as n goes to infinity, as long as p is bigger than 0. So we're going to assume 6% interest. So that goes away, so the annuity is worth just that, m times 1 plus p over p, because the limit as n goes to infinity of 1 over 1 plus p to the n minus 1, that's going to 0. So the value for m is $50,000, and at 6%, v is only $883,000. All right? So you're better off taking $1 million today than $50,000 a year forever. Now, if you think about it, and think about it as an interest rate, why should it be obvious that you're better off with $1 million today than 50 grand a year forever? Think about what you could do with that $1 million if you had it today at 6% interest. What would you do with it to make more money than 50 grand a year forever? Yeah? Yeah, in this model, if the interest rate is 6%, you can put it in the bank, make 6% every year. That's 60 grand a year forever. Better than 50 grand a year forever. All right, so maybe it's, you know, even without doing the math, you can tell which way it's going to go. But this tells you exactly what it's worth. All right? Any questions? Okay. Yeah.
That's how much it's worth to you right now.
Yeah.
So it might be like if you have $1 in the future.
Yeah.
Where as right now it's like M over 1 plus P.
Yeah.
It's worth less to you. Yet later on it's going to be worth more to you.
So if you move yourself forward in time, $1 in a year will be worth $1 to you. But today, it's worth less than $1 to you because you could take the dollar today and invest it in the bank, and it's worth more in a year because the money grows in value. Is the way to think of it, because you can earn interest on it. What's that? Yeah, if you just spend it, well, then at least you had the use of what you spent it on for the year. So there's some other kind of value, right? Maybe you bought a house, or something that even appreciated in value. Okay, but yeah, these things get sort of squishy, and that is where a lot of people make money on Wall Street, is because different companies have different needs for money. They have different views of what the interest rates are going to be, and you can play in the middle. All right, make a lot of money that way. Okay. All right, so more generally, there's a corollary to the theorem, and that is that if the absolute value of x is less than 1, then the sum I equals 0 to infinity x to the I is just 1 over 1 minus x. All right, and we didn't prove this back in the second recitation because there's no n to induct on here. But the proof is simple from the theorem. And it's simply because if x is less than 1 in absolute value, as n goes to infinity, that goes to 0. And so you're just left with 1 over 1 minus x. Okay. So for example, what's this sum? This one you all know, I'm sure. Out to infinity, what's that sum to? To 2, yeah. It's 1 over 1 minus a half, which is 2. What about this sum? Out to infinity, what does that sum to? Yeah, 3 halves. 1 over 1 minus a third is 3 halves. All right, so easy corollaries. These are all examples of geometric series. That's what a definition of a geometric series is. Something is going down by a fixed, each term goes down by the same fixed amount every time. And geometric series generally sum to something that is very close to the largest term. In this case, it's 1. Very common. Because of that formula, it's 1 over 1 minus x. Any questions about this or geometric series? All right. Well, those are straight geometric sums. Sometimes you run into things that are a little bit more complicated. For example, say I have this kind of a sum. I equals 1 to n. I times x to the I. In other words, we're adding up x plus 2x squared plus 3x cubed and so forth up to n x to the n. That's a little more complicated. The terms are getting, decreasing by a factor of x, increasing by 1 in terms of the coefficient every time. A little trickier. So say we wanted to get a closed form expression for that. There's several ways we can do it. The first would be to try to use perturbation, the perturbation method. So let's try that. So we write s equals x plus 2x squared plus 3x cubed plus n x to the n. And let's try the same perturbation. Multiply by x. I get x squared plus 2x cubed plus n minus 1 x to the n plus n x to the n plus 1. And then I subtract to try to get all the cancellation. So when I do that, I get 1 minus x times s. Oh, I didn't quite cancel everything. X plus x squared plus x cubed plus x to the n plus n, or minus n x to the n plus 1. It didn't quite work. Anybody see a way that I can fix this up? What about this piece? That's still a mess here. Can I simplify that? Yeah? Yeah. There's a simpler way. Yeah?
That's a geometric series.
That's a geometric series. We just got the formula for it. So that's easy. This equals 1 minus x to the n over 1 minus x minus the 1, because I'm missing the 1 here. So we can rewrite this whole thing over here. Oops, yikes, got attacked. What's that? Yes, it would. That's right. I got to add 1 to there. Okay, so that's good. So that says that 1 minus x times s equals 1 minus x to the n plus 1 over 1 minus x minus 1. And then I got to remember to subtract that term too. Minus n x to the n plus 1. That means now I just divide through and I simplify, divide through by 1 minus x and simplify, and I get the following formula. I won't go through all the details, but it's not hard. Let's see if I got that right. Yeah, that looks right. Okay, so that is the closed form expression for that sum, which we can get from the perturbation method in the fact that we'd already done the geometric series. All right, there's another way to compute these kinds of sums, which I want to show you because it can be useful. So we're going to do the same sum and derive the formula a different way. This method is called the derivative method. And the idea is to start with the geometric series, which it's close to, and then take a derivative. So for x not equal to 1, we already know from the theorem that I equals 0 to n x to the I equals 1 minus x to the n plus 1 over 1 minus x. That was the theorem. We already know that. Now I can take the derivative of both sides. And let's see what we get by taking the derivative. Well, here I get the sum. The derivative of x to the I is just I times x to the I minus 1. The derivative over here is a little messier. I got to have, well, I take 1 minus x times the derivative of that. Derivative of this is now minus n plus 1 x to the n. Then I take this times the derivative of that is now minus 1 minus x to the n plus 1. And then I divide by that squared. Now when we compute all that out, we get this. 1 minus n plus 1 x to the n plus n x to the n plus 1 over 1 minus x squared. All right, I won't drag you through the algebra, but it's not hard to go from there to there. This is pretty close to what we wanted. We're trying to figure out this. And we almost got there. What do I do to finish it up? Multiply by x. Good. So if I take this and multiply by x, I equals 0 to n, I x to the I equals x minus n plus 1, x to the n plus 1, plus n x to the n plus 2, all over 1 minus x squared. Okay? Which should be the same form that we had up there. All right, so that's called the derivative method. You can start manipulating. You treat these things as polynomials, these sums, and you start manipulating them like you would polynomials. In fact, there's a whole branch of mathematics called generating functions that we won't have time to do in this class. That's in chapter 12 of the text. But you do things like that to get sums. Any questions about what we did there? You can also do a version where you take integrals of this if you want. And then you get the i's in the denominator instead of as coefficients. For homework, I think we've given you the sum of I squared x to the I. How do you think you're going to do that? Any thoughts about how you're going to solve that? Get the sum, a closed form for the sum of I squared x to the I?
Do the derivative method twice.
Yeah, do it twice. Take this, which now you know. Take the derivative again. All right, won't be too hard. All right. You can also take the version of this where n goes to infinity. Let's do that. If the absolute value of x is less than 1, the sum I equals 1 to infinity of I x to the I, what does that equal? This one you can see it easier up here. What happens when n goes to infinity? What does this do? X is less than 1 in absolute value. What happens to this as n goes to infinity? This term. What goes to 0. Right? This gets big, but this gets smaller faster. What happens to this term as n goes to infinity? Same thing, 0. All I'm left with is x over 1 minus x squared. All right, now this formula is useful if you're trying to say get the value of a company. And the company is growing. Every year, the company grows its bottom line by $m. So the first year, the company generates $m. The next year, it generates $2m in profit. The next year is $3m. So you got an entity that every year is growing by a fixed amount. It's not doubling every year, but every year adds in $m more of profit. What would you pay to buy that company? What is that worth? All right, so you can think of this as, again, an annuity. Here, the annuity pays $im. In this case, at the end, not the beginning, say, of year I, forever. This company is, or this annuity is worth, well, we just plug into the formula. Instead of $1 each year, it's m, so there's an m out front. X is 1 over 1 plus p. And then we have 1 minus 1 over 1 plus p squared. And if we multiply the top and bottom by 1 plus p squared, we get m 1 plus p over p squared. All right, so it's possible with a very simple formula to figure out how much you should spend to buy this company, what its value is today. So for example, say the company was adding $50,000 a year in profit. The interest rate was 6%. The value of this company is $14 million, $14.7 million. Just plugging into that formula. All right, so people that buy companies and stuff, they use formulas like this to figure out what it's worth. Of course, you got to make sure it's really going to keep paying, the $50,000 more every year, and that this is the right interest rate to be thinking about. And the guys on Wall Street, the bankers on Wall Street, they all have their estimations for what these things, are, the value of P they would put into these formulas. Any questions about that? Yeah. Okay, good. All right, so this one is okay? Okay. I plugged x equals 1 over 1 plus p, like we did before, remember, for the annuity, because every year you're degrading it, devaluing it by 1 over 1 plus p. So that's the x term. And it's paying, in the ith year, it's paying IM dollars. All right? So the first year it pays M dollars. The next year 2M. The next year 3M. The next year 4M. But every year you're knocking it down by 1 plus 1 over P to the number of years. So what you get, the sum you've really got here, is I equals 1 to infinity. IM dollars are paid, but those dollars are worth 1 over 1 plus P to the I today, the current value. That's a good question. I should have said that. That's a great question. All right? So that's how we connected this up, because you're getting paid this much in I years, and that's worth that much degradation or that much devaluation today. And now we add up the total current value. All right, so even a company that is paying you more and more every year still has a finite value, because the extra, the payments are increasing, but only linearly. The value today is decreasing geometrically. And the geometric decrease wipes out the value of the company in the future. Yeah? Where should I, what did I do? Oh, wait. I screwed up here, too. Is that what you're asking about? Yeah, that's what I should have done, right? Because I got 1 minus x is 1 minus 1 over 1 plus p. That gets squared. And now when I multiply 1 plus p squared, it's multiplying this by 1 plus p. It's 1 plus p minus 1 is p. So I have p squared. All right, so this part's OK. That part I wrote wrong. That's good. Any other questions? All right. OK. So let's do a simple example. What is this sum? A half plus 2/4 plus 3/8 plus 4/16 forever. What's that sum equal? You can plug that in the formula. Yep. That's right. Good. These details. Yeah, otherwise that sum would be what? If I didn't put the negative here, it's going to be infinity. That's not so interesting. The negative makes it more interesting, so I got 1 over 2 to the I in there. What's it worth then? I can plug it in the formula. What's x? 1/2. So I get 1/2 over 1 minus 1/2 squared is 1/2 over 1/4, and that's 2. Okay. All right. Any questions on that formula? Okay. It's amazing how useful these things get to be later. All right. So that's sort of the geometric kinds of things. Next, I want to talk about more the arithmetic kinds of sums and what you do there. In fact, we've already seen one that we've done. If I sum I equals 1 to n of I think we've already done this one. That's just n times n plus 1 over 2. And probably most of you even learned that formula back in middle school, I'm guessing, maybe before. How many people know the answer for this sum? The sum of the squares, the first n squares, all right? Somebody knows. What is it?
N times n plus 1 times 2n plus 1 all over 6.
All right, very good. That is correct. All right, most people don't remember that one. It's a little harder to derive. How would you prove this? By induction. Unfortunately, induction doesn't tell you how to remember what the formula was. And there's a couple of ways you can go about that. One is you could remember or guess that the answer is a polynomial in n. In fact, because you're summing squares, you might guess that it's a cubic polynomial in n. And if you remember just that or guess just that, then you could actually plug in values and get the answer. And this is, a common method of solving these sums is you sort of guess the form of the solution. In this case, you might guess that for all n, the sum I equals 1 to n of I squared equals a cubic. And then what you would do is plug in the value n equals 1, n equals 2, maybe even we'll make it n equals 0, make it simple, and start getting some constraints on the coefficients. So you would plug in n equals 0, the sum is 0. The polynomial evaluates to d. That tells you what d's got to be right away. N equals 1, the sum is 1, and when you plug into the polynomial, you get a plus b plus c plus d. N equals 2, well, that's 1 plus 4 is 5. 2 cubed is 8, so you'd have 8a plus 4b plus 2c plus d. And you'll need one more since you got 4 variables. Let's see, 1 plus 4 plus 9 is 14. I've now got 3 cubed is 27a plus 9b plus 3c plus d. So now I got 4 equations and 4 variables, and with any luck, I can solve that system of equations and get the answer. And in fact, you can. When you solve this system, you get a equals 1/3, b equals 1/2, c equals 1/6, and d equals 0. And that's exactly what you get in that formula. So that's a way to reproduce the formula if you forgot it. Now, this method, really to be sure you got the right answer, you got to go prove it by induction. Because I derived the answer if it was a polynomial, I would have gotten it right, but I might be wrong in my guess. And to make sure your guess is right, you got to go back and use induction to prove it for this approach. Yeah?
And not some higher powers.
Well, it turns out that anytime you're summing powers, the answer is a polynomial to 1 higher degree. So if you just remembered that fact or you guessed that fact, another way to sort of imagine that might be true is that you know, I'm getting n of them, so I might be multiplying. And the top one is n squared. So I'm going to have n of them about n squared, maybe something like n cubed. That's another way, you know, you could think of it to guess that. Any other questions on this? OK. All right. So far, all these sums had nice closed forms. And a lot of them do that you'll encounter later on, but not all. And sometimes you get sums that don't have a nice closed form. At least nobody's ever figured out one, and probably doesn't always exist. For example, what if I want to sum the first n square roots of integers? Let's write that down. So say I want a closed form for this guy. You know, nobody knows an answer for that. But there are ways of getting very good close bounds on it that are closed form. And these are very important. We're going to use this the rest of today and the rest of next time. And they're based on replacing the sum with an integral. And the integral is very close to the right answer, and then we can see what the error terms are. So let's first look at the case when we've got a sum where the terms are increasing as I grows. All right, and these, we'll call these integration bounds. And a general sum will look like this. I equals 1 to n of f of I. And the first case is when f is a positive increasing function. Increasing in I. All right, integration bounds, and so we're increasing function. All right, so let me draw a picture that'll hopefully make the bounds we're going to get pretty easy. So let's draw the sum here. As follows. I got 0, 1, 2, 3, n minus 2, n minus 1, n. And draw the values of f here. Here's f of 1, f of 2, it's increasing, f of 3, f of n minus 1, and f of n. Then I'll draw the rectangles here. So this has area of f of 1. This has area f of 2. This has area f of 3. And we keep on going. Let's see. This will be f of n minus 2 on this one. I'll just do f of n minus 1. Draw this guy here. So its unit width, its height is f of n minus 1. So its area is f of n minus 1. And then f of n. All right, and let me also, so the sum of f of I is the areas in the rectangles. That's what the sum is. And I want to get bounds on this sum using the integral, because integrals are easier to compute. So let's draw the function f of x from 1 to n. All right, so this is f of x as a function. Now I claim that the sum I equals 1 to n of f of I is at least f of 1 plus the integral from 1 to n f of x dx. Now the integral from 1 to n of f of x is this stuff, the stuff under the curve. All right, comes down here, starts at 1, and it's the stuff under the curve. And what I'm saying here is that if you take that stuff under the curve and add f of 1, which is this piece, that's a lower bound on our sum. The sum's bigger than that. All right, so what I'm saying is the area in the rectangles is at least as big as the area in the first rectangle plus the area under the curve. Does everybody see why that is? All right, I'm saying the sum is the area in the rectangles. All right, that's pretty clear. And that is at least as big as the first rectangle, f of 1, plus the stuff under the curve, which is the integral. And I've chopped off these guys. That's extra. OK? Is that all right? It's a lower bound? Any questions on the lower bound? This is a picture proof, all right, which we always tell you not to do, but we're going to do one here. And of course, it totally hides what why did I need f is increasing, but we'll see that in a minute. The proof would not work unless it is increasing here. All right. Any questions? Because now I'm going to do the other bound, the other side. All right, I also claim, this will be a little trickier to see, that the sum is at most f of n plus the integral from 1 to n. All right, so this is the lower bound, add in f of 1. The upper bound, just add in f of n. So let's see why that's true. Now, to see that, I'm not going to be able to draw it. I want you to imagine taking this curve and the area under it down to here and sliding it left 1 unit. All right, sliding it left to here, sliding it left 1 unit over to here. Now, when I slide it left 1 unit, did the area under it change? No. It's the same area under it. Just where it sits on the picture is now out here. All right, it's this area under this guy, but it's the same thing. It's the same integral. And you can see that it's more than what's in these rectangles, because I got all this stuff. And of course, I didn't even include this, so now I add the Fn. So if I take the area under the curve, which is the integral, shifted left 1, so it only goes up to here now, and then add in this rectangle, that dominates the area in the rectangles. Bigger than. All right, you see that? I could do a lot of equations on the board, but for sure that would be hopeless to follow. Any questions about this? Yeah?
I guess I understand the lower bound because we're cutting off the triangles. So
Yeah.
But is it a lot of hand waving, or am I just missing something that it's always going to be the F of n?
Yeah, there's a little hand waving going on, but I do believe it's true. We can, with equations, you can make it precise. So let's look at it again. Do this one more time. Yeah, I'm waving hands a little bit, but it also, hopefully the intuition comes across. Because when I shift left by 1, this point becomes this point. That point becomes that point. And I'm catching the sort of the cusp of these rectangles. And now I take this curve here, shifting the whole curve left 1 unit. And the area doesn't change. It would be equivalent of taking the integral from 0 to n minus 1, is what I'm doing, of f of x plus 1. All right, there's another way to look at it mathematically, maybe probably the formal way to do it. But the idea is that this now contains all these first n minus 1 rectangles are contained underneath it. And then I just add this in, and I'm good to go. I've contained all the rectangles now for the upper bound. All right, mathematically what this curve is 0 to n minus 1, fx plus 1, which is the same thing as what that is. Okay? Any questions for that? All right, but now I have good bounds on the sum. Right? We know that the sum is at least this, and at most that. And those two bounds only differ by a single term in the sum. So they're very close. All right, and these actually are good formulas to write down for your crib sheet. That is worth doing on the test. And we'll use them more today, and we'll also use them on Thursday. Okay, so now we can actually get close bounds on the sum of the square roots. All right, so let's see how this works for f of I equal the square root of I, which is increasing. So I compute the integral from 1 to n of square root of x dx. And that's just x to the 3 halves over 3 halves, evaluated at n and 1. And that just equals 2/3 n to the 3 halves minus 1. And now I can compute the bounds on the sum of the first n square roots. All right, so I know that square root I equals 1 to n. Well, the upper bound is fn plus the integral. And the lower bound is f of 1 plus the integral. What is f of n? That's the square root of n. What is f of 1? Square root of 1, which is 1. All right, so I'll plug that in here. I get 2/3 n to the 3 halves plus 1 minus 2/3 is plus 1/3. And here I get 2/3 n to the 3 halves plus the square root of n minus 2/3. All right, so now I have pretty good bounds on the sum of the first n square roots using this method. So for example, take n equals 100. This number evaluates to 667. This number evaluates to 676. And the difference is 9, which is the square root of 100 minus 1. This is square root of n. This is 1. So the gap here is square root of n minus 1. And n equals 100. Square root of 100 minus 1 is 9. So I shouldn't be surprised my gap here is 9. So I didn't get exactly the right answer, but I'm pretty close here. Now, as n grows, what happens to the gap between the upper bound and the lower bound? What does it do? It gets bigger. So my gap gets bigger. Well, that's not so nice. It doesn't always stay 9 forever. But somehow, though, this is still pretty good because the gap grows, but the gap only grows as square root of n, where the answer, the bounds, are growing as n to the 3 halves. In other words, my error is somewhere around here, and that gets smaller compared to my answer, which is somewhere around there. All right, and there's a special notation that people use. In fact, let's write that down and then do the notation. Another way of writing this is that the sum I equals 1 to n of square root of I. The leading term here is 2/3 n to the 3 halves. And then there's some error term, delta term here. Call that delta n. And we know that the error term is at least a third, and at most square root of n minus 2/3. All right? So this delta term is bounded by square root of n. That's getting bigger as n gets big, but this value compared to your answer is getting small. That's nice. And so the way that gets represented is as follows. We would say, it's using the tilde notation. We write tilde 2/3 times n to the 3/2. And now we've gotten rid of the delta because this tilde is telling us that everything else out here gets small compared to this as n gets big. And the formal definition, let's write out the formal definition for it. Now, a lot of times you'll see people use this symbol to mean about. That's informal. When I'm using it here, it's a very formal meaning mathematically. A function g of x is tilde a function h of x means that the limit as x goes to infinity of g over h is 1. In other words, that as x goes to infinity, as x gets big, the ratio of these guys becomes 1. All right, and let's see if that's true here. All right, well, square root of I equals this, so I need to show the limit of this over that is 1. So let's check that. The limit as n goes to infinity of 2/3 n to the 3/2 plus that delta term over 2/3 n to the 3/2. Well, that equals, divide out by 2/3 n to the 3/2, I get a 1. Should I have subtracted? No, that's okay. 1 plus delta n over 2/3 n to the 3/2. I can pull the 1 out front. That's 1 plus the limit. And this is now, delta n is at most square root of n. So I get square root of n over 2/3 n to the 3/2. Square root of n over n to the 3/2, that goes to 0. So this equals 1. All right, so this limit is 1, and so therefore I can say that the sum of the first n square roots is tilde 2/3 n to the 3/2. Any questions about this? We're going to do a lot of this kind of notation next time. Yeah?
And got 2/3 n to the 3/2 minus 1. Why did the minus 1 not become part of the actual solution, become part of the delta?
Okay, so you brought it up to here, right? Okay, so then I plug that in to the integral. It appears on both sides here, and here I add the f1, here I add the fn. And now I have the lower bound here and the upper bound here. Are you good with those? All right, now some judgment takes place. And what I'm really trying to do here is figure out what are the important terms in these bounds as n gets big. How big is this growing as n gets big? Well, as n gets big, the third is not doing much. As n gets big, the square root of n grows, but it's nothing like what's happening here. If you had to describe to somebody what's going on in this bound, would you start here or here? No, you'd start here. This is the action, and there's a little bit, the rest is just in the slop, in the air. And so now I've used judgment to say the delta is somewhere in this stuff here. All right, what's really happening, and the nice thing is they match. The lower bound and the upper bound match on that term. So what I do is I write it equals this term plus something that's smaller. And in particular, it's between 1/3 and square root of n minus 2/3. All right? So what I'm trying to capture here is just the guts of what's happening to this function as n grows. And the guts of it is this. It's not exactly equal to 2/3 times n to the 3/2, but it's close. And in fact, if I take the limit of this over that, that limit goes to 1. It's a way of saying they're approximately the same, or that's called asymptotically the same. And we'll talk a lot more about asymptotic notation next time, where we'll give you 5 more symbols besides tilde that people use. But, all right, any questions about, maybe start with the bounds. Any question on the bounds that we got? That's the integration method, first getting the bounds. You take the integral, you add f of 1 for the lower bound, you add f of n for the upper bound. And it's in between, somewhere in there. Questions there? All right, then we plugged it in, and now we look at this tilde notation that says, well, first we write it like this. The sum is this value plus an error term, and lo and behold, that error term is small. If I take the limit of the whole thing divided by the big term, I get 1, which means this thing is really not important. So I write this. Questions on that? All right. All right, there's one more case to consider. And now we're going to go back to the integration bounds, and that is when f is a decreasing function. And we're going to do the analysis for that, and then we'll be all done. So we're going to look at integration bounds when f is decreasing and positive still. All right, and the example here might be, for example, the sum I equals 1 to n, 1 over the square root of I. Say you had to get some idea of how fast that function is growing as a function of n. I'm summing the first n inverses of square roots. What is that roughly going to be? How fast does that grow as a function of n? All right, so let's do that. And of course, 1 over square root of I decreases as I gets bigger. So let's do the general picture again. See what happens. So we have 0, 1, 2, 3, n minus 2, n minus 1, n. And now f of n is the small term. And f of n minus 1, f of 3 here, f of 1. Now I'm going to draw the rectangle. This has area f of 1. This one has area f of 2. This one has area f of 3. And then this one has area f of n minus 1 here. And then lastly, area f of n. So the sum is the area in the rectangles, just like before, except now the rectangles are getting smaller. Let's draw the integral like we did before. The integral is the area under this curve, f of x here, just like before. So this is f of x, only it's decreasing. Now, let's take the area under this curve and add f of 1 to it. If I take the area under this curve all the way down to here and then add f of 1, what do I get? upper bound on my sum. Okay, so the sum I equals 1 to n, f of I, is upper bounded by that guy, which is f of 1, plus my integral, which is the area under the curve. The integral is the area under that curve, starting here, and that contains all these rectangles. And then I just add in f of 1 to get an upper bound. All right. Now for the lower bound, think about shifting the whole curve left by 1. That goes to there. This goes to here. That goes to here. That goes to there. And that goes to there. The area under the curve did not change when I shifted it left by 1. This is now my area under the curve. Stops here. What do I get when I take that area and add in this last box, f of n? A lower bound, right? Because it's contained in all the rectangles. Now, what's really weird about these formulas? Do they look familiar? Yeah. Yeah? I switched them. Yeah, they're the same formulas we had over here, except we switched the direction on the less than and greater than signs. Or I swapped f of 1 and f of n, however you want to think about it. The lower bound here, in that case, became the upper bound in this case. I mean, is that possible that the lower bound became the upper bound? Yeah, yeah. Because what really happened here, which is the big term in this case, fn or f1? f1 is the big term because it's decreasing. So it's totally symmetric. All right? The proof was very similar. So the nice thing is you only got to remember the bounds are now simple. For any sum, as long as it's increasing or decreasing, it's the same as the integral. The lower bound is the smaller of the first and last term, and the upper bound is the larger of the first and last term. Very easy to remember. Probably don't even need the crib sheet for it, although to be safe, I want to write that down. So now it's easy to compute good bounds on the sum of the inverse square roots. Any questions there before I go do it? OK. So let's take the case where we're summing 1 over square root of I. So we compute the integral of 1 over square root of x dx. That equals the square root of x over a half, evaluated at n and 1. That equals 2 square root of n minus 1, or 2 square root of n minus 2. And now we can bound the sum. The upper bound is f of 1 plus the integral. The lower bound is f of n plus the integral. What is f of 1? 1. 1 over the square root of 1 is 1. What is f of n? 1 over the square root of n, small. All right, so these bounds are pretty close here, right? In fact, this gets really tiny as n gets big, so I'm just going to replace this with 2 square root of n minus 2 and make it a strict lower bound. And this, cancel there, I get 2 square root of n minus 1. Wow, these bounds are great. They're within 1 for all n. That's really good. OK, so we can rewrite this in terms of the what really matters. What really matters in these bounds? How fast is this function growing?
2 root n.
2 root n. That's what really matters. So let's write that down. All right, so this says that the sum I equals 1 to n of 1 over square root I equals 2 square root of n, we have a minus delta n, where delta is between 1 and 2. And so if I use the tilde notation, what would I write down here for the tilde? Past the tilde. I don't want to mess, I don't want to keep track of all the delta stuff as n gets big.
2 root n.
2 root n. Because this term over that goes to 0 as n gets large. So let's just check that. So we take the limit as n goes to infinity of 2 root n minus delta n over 2 root n. Just checking the definition now. That's what the definition would be. Equals 1 minus the limit as n goes to infinity of 2 over 2 root n. This is 0. So it equals 1. And so now you know that the sum of the first n inverse square roots grows as 2 root n, which is the integral. Yeah?
Off the lower bound, the f of n was 1 over root n.
Yeah, I dropped it off because it's so tiny and going to 0 and just made a strict less than. In fact, yeah, so I don't hurt myself by dropping it off. In fact, the lower bound was a little bit, I made a little weaker lower bound. So this is still true. It wasn't as tight as it used to be, so I could keep it around. Yeah, it doesn't hurt to keep it around, then it's less than or equal there. And now this would be something like that. So I could keep it around, but I'm going to get rid of it anyway because I'm going to go to the tilde notation. And this, as n gets big, this is really tiny. So in this case, the bounds are great. You can nail it pretty much right on. Yeah?
So 1 over root n is still there. The number is bigger than it would normally be. So when you take it out, it becomes smaller. So how could you go to a less than and like avoid the less than or equal to?
Well, you're saying you don't like the fact that I dropped it here?
Yeah, like when you drop it, why do you go to a less than instead of less than or equal?
Oh, because I've got a bigger bound that I made less when I dropped it. I took something away, so I know I could never equal this because I know it's bigger than this. I know that the real answer has to be at least this big, and so it has to be bigger than something smaller. That's why I did it. Okay, any other questions? All right, we'll get more practice tomorrow and next time with this stuff.